And we'll start from current slide. And let me just make a couple of one major announcement, I guess, before we get going. I know most of y'all don't come around looking for me on most times during office hours, but just to let you know in case you were going to, normally I have office hours on Friday mornings on the Birmingham West Campus from 8 to 12. Friday morning I've got an eye appointment, but I thought it was going to be at Eye Foundation Hospital, but it's at UAB West. I didn't know they did appointments out there, but anyway, that's right across the street from the West Camp, the Western campus of Lawson, so that's where I usually am. So I'll just drive out there, have my appointment, and then come back here. So I'm guessing I'll be back here somewhere close to 10 o'clock, maybe earlier if they get through in a hurry, or maybe later if things drag on. So, but I'm hoping to be there by 10, and then we'll go on from there. All right, any questions on anything we've covered so far? Anything? Okay. If not, we are in Chapter 16, which is Wave, Motions, and Sound, and we were just about ready to do Example 1 in Section 16.2. Very, very short section, and this is the one and only example in this section. They have several problems, but only one example. This says, this is on page 434 if you're following in the text. The FM band of a radio is centered around the frequency of 100 megahertz. Okay. Oh, let me get my pen adapted. Okay. 100 megahertz. Oops, that's capital MHZ. Goodness, I can't write. Okay. Let me get that corrected and that corrected. Okay. Let's try it one more time. Megahertz. HZ. The pen's still dragging some. Okay, so what is this? Centered around a frequency. So this is the frequency. Okay, of 100 megahertz. Now, does anyone remember what mega stands for in the metric system? Million, exactly. It's 1,000,000 hertz. That's a pretty high frequency, 100 megahertz. Okay, FM is on the high frequency bit. It says find the length of an FM antenna. So we want the length of the antenna. Okay, length of the antenna if each arm must be a quarter wavelength. Okay. So then it says first find the wavelength. Good idea. So how is wavelength related to frequency?
Sound, I guess. I don't know. It measures frequency.
Second?
It measures frequency. The wavelength measures frequency.
No, frequency is cycles per second. Wavelength is some length. So those are not the same measures. They're related through, and it's sort of a roundabout way, but related through the wave speed. Okay? Because wave speed, if you think about wave speed, this is in basically a megahertz is 10 to the 6th, and it's per seconds, 1 over seconds, okay? Wavelength is measured in meters, okay? Now, what relates meters to per seconds? Velocity. Meters per second is, okay, so here is the thing. Now, in general, the velocity of a wave is equal to its wavelength times its frequency. You get meters per second. Yeah, that's a good velocity. But when we're dealing with FM, AM, light, any kind of electromagnetic radiation, what is the velocity? You might want to turn back one page and you see the formula there. See it? C is equal to wavelength times frequency. And what is C? Speed of light. Speed of light. And they give it to you here as 3. Okay, now, before I do that. All right. Now, the question here is your preference. We're looking for the wavelength. That's what we're looking for. This is the unknown for right now. Okay? So, do you want to solve this equation for wavelength before you plug the numbers in, or you want to plug the numbers in now and then try to determine the wavelength? I really don't care much one way or another. You tell me. Second, solve for the wavelength. So we're wanting to solve for this, so what would we do? And it's already multiplied. Divide both sides by the frequency. Or if you like doing the triangles or circles, I'll just show you again, whichever you prefer. They're exactly equivalent to each other. Since you know that C is equal to wavelength times frequency, you know that then wavelength is equal to C divided by frequency, which is exactly what we found. So C, from the previous page they give it to you, is 3.00 times 10 to the 8th meters per second, divided by the frequency, okay? And 100 megahertz is 100 times 10 to the 6th, right? Meters. No, I'm saying per second, sorry. I'm already giving my answer. Per second. So I'll write this time as just a per second. So you see here the per seconds go out. Now if you wanted to adjust that denominator, you can move this decimal 2 more places to the left, making a smaller number here if you increase this by 2 and making that an 8. And now you got 3 divided by 1. I can do that. What would that be? Not 30, 3. Oh, I thought you said 30. Okay. But it's 3.00 because we have 3 significant digits everywhere. 3.00 meters. So that's how long the wavelength is. What is the length and what they're asking for? I wish they had a picture because this isn't making a lot of sense. Find the length of an FM antenna if each arm must be a quarter of a wavelength. So how many arms do they have? I don't know. I'm guessing 2. Yeah. So I'm guessing 1 arm on each side. And if that's a quarter of a wavelength here and a quarter of a wavelength there. That's my best guess. I don't know. They don't have a picture, so I'm guessing at it. So this is 1 wavelength. What would be a quarter of that? That would be, divide by 4. 3/4 of a meter or 0.750 meters. Okay? Now, if that's each arm, if they have 2 arms, then this would be 2 arms would be 1.50 meters. I don't know which one it is. Let's see what they got in the book. Nope, they just have 1 arm. Okay, so just leave it at the 0.75. It wasn't a very clear question in my mind. If each arm must be a quarter wavelength. So that's what they're looking for. 1/4 of 3 is 0.750 meters. Very good. Now, they have a figure here in your text on the electromagnetic spectrum. And does anyone need this up a little longer?
Yeah.
Okay. All right. I'll leave it there for a bit. And there is a similar type figure on the slide set, so I was going to do that. Goodness, by the middle of the week, I'm running out, especially daylight saving time. My word, my body doesn't want to go to bed before the old time, but it has to get up on the new time, so it seems like every night I lose another hour's sleep. But it's getting better. I'm getting so tired at night that I will go on to sleep at a better time anyway. Yeah. All right, ready? Finished? So let's close this one out.
You sure wake up in the morning like, dog, already?
Yeah. I get up pretty early, and of course it's dark, but then usually after my shower and everything else, I come out, it's still dark. And at least in the old time, it was beginning to get light by then. So come on, give me a break here. But it is changing slowly. Okay. So let's go from current slide here. And this is the one pretty much exactly like in the book. All right. This is your electromagnetic spectrum. And the frequency is getting greater as you go that way. These are cycles per second, which is hertz, basically. It's just per second. Okay? And the one we were just looking at was 100 megahertz, which was 10 to the 8th hertz. Okay, so it's right in here. That's TV and also FM radio. Yeah. Your AM radio is usually down this way, a little ways from there.
Why is it so much of a difference?
What's that?
Why is it such a difference?
Why is there a difference? Well, it's the type. Well, first, what AM stands for is amplitude modulation. FM is frequency modulation. There are different types of things. But to answer your question, they assigned these wavelengths in chunks, and they had AM already assigned down here. It had other things assigned somewhere else. That's the broadcast band, by the way, AM. And they have shortwave radios here, which are the ham operators and stuff, and they had a chunk. So when they went to do FM, they needed to get somewhere outside of these bands, so they went up here to this one. Now, there's advantages and disadvantages to both of those. The higher the frequency, the shorter the wavelength, but the higher the frequency it is, those waves don't tend to bend as much as a longer wavelength tends to bend a little more. So therefore, an AM antenna, an AM station, will actually broadcast for much greater distances than FM, similar power. Now, they boosted the FM up, so they give you pretty good, but they're still line of sight, pretty much. They don't bend much. AM will bend. So those FMs, they drive down Birmingham, up on Red Mountain, the highest point anywhere around Birmingham. You see all these antennas up there because that gives them a greater line of sight, so they get broader coverage. Now, I don't know where things like 3340, they have one antenna in one place and one in some other place, so they get better coverage that way. So
like Sirius XM, they pick up coverage.
What's that?
Where you live.
Who's this?
Like Sirius XM, like the radio station.
Now that's satellite. Yeah,
okay.
And the satellites are up there. And,
I was saying they gotta have antennas everywhere.
Well, no, they're real tall antennas. They're up on satellites, out in outer space. So yeah. Okay. But these are the radio waves. They're sort of, we think, 100 million megahertz, or 100 megahertz, which are 100 million hertz. That sounds like a pretty high number, but look at these other numbers. Those are much higher frequency. In fact, visible light is much higher frequency, much shorter wavelength. By the way, as your frequency is going up, your wavelength is going down. Okay, but let's see where we were before. 10 to the 8th. What did we get? Right around 3 meters, and that's exactly what we got in New Hampshire, and then a third of that. So yeah. These are rather long radio waves. Now, the AM stations, which are down here, they have to be well, maybe not 300 meters. That's 3 football fields, you know, in length. And they can't have antennas quite that long, but they can be fractions of that. So those are very long wavelengths. Okay, 3 meters is basically the height of the ceiling here, maybe pretty close to it.
So the infrared light, I guess it can reach pretty far too, right? Because I just seen a story about the NFL catching somebody that was pointing one at, was it Tom Brady or something?
Right.
And I guess they had to be pretty far back in the crowd to be able to point and it show up on his eyes.
Oh, really?
Yeah.
Huh. Well, actually, I think that was laser.
Was it a laser?
Yeah,
I think
it
so.
had to be laser.
Yeah, that sounds like a laser pointer.
Okay.
Yeah.
So what is the infrared?
Infrared is basically heat radiation.
Okay.
Yeah,
Okay.
right.
But that's still pretty far, right? With a laser, right?
Oh yeah, but you see, a laser, I can't remember exactly what that stands for. That's a long name that they shorten with just the abbreviation laser. But what you have is a very synchronized frequency, so it's really intense, so therefore it stays in a very straight beam. So yeah,
It
it's
just stop wherever you aim it.
yeah. And that's why don't let kids play around with laser pointers, because if they point them to the eye, you can burn a retina.
Well, see,
so
that's why they was trying to charge that guy, whoever they found with crime.
Also trying to
They say he laser Tom Brady.
To distract him on the football field.
and after all,
And nobody saw it.
Not until somebody, yeah. It came up somehow that they ended up finding out who it was, but
Did they go back to the videos and like see the laser in his
they
face?
see the laser on his eyes, yeah.
I got to see one of my cousins. He loved Tom Brady. He was just
I have a niece who's married to Tom Brady.
really?
Not that Tom Brady.
She married to a Tom Brady.
A Tom Brady. And when she said that somewhere, first being introduced to someone, someone said, "You looked a lot different on television." And she took that as, well, I bet you his wife is quite a looker. I don't know who his wife is, but my guess. So anyway, infrared is heat radiation. This is visible light. And the amazing thing about our really fantastic atmosphere, all this radiation is really dangerous stuff, deadly stuff. Gamma rays will kill you. X-rays will really do a lot of damage if done too much. Ultraviolet rays cause cataracts, which I have to go get my eyes checked Friday. They cause skin cancers, okay?
Yeah.
So those are not nice rays either. Our atmosphere blocks just about all these, most of those. There's some ultraviolet gets through, and basically only allows the visible light in, which is fortunate for us because that's not harmful to us. Now, this other stuff can come and go, it's lower energy, but that's the main.
So I wonder how much would the X-ray affect the actual person that's doing the test?
They
Compared
always stay
to-
out the way.
Yeah, they do, but
That's why they get behind those windows. Those are leaded glass windows. Lead blocks a lot of that. And those walls, I guarantee you, there's lead built into those walls. And that's why they get behind that. And they also wear some type of a badge to measure the radiation. If they exceed what they're allowed in a month, they can't come back a week to work for that month.
Oh my goodness.
Yeah, so that is a really serious deal there. And those technicians, they don't stay in the room when that's on. They get away because they're around it all the time. You're only, and that's over with. But I don't know if y'all remember a shoe brand called, I think it was Keds.
Yeah, kids.
And there was a company that they either had their own stores or some store that marketed Keds. Back when I was young, they said, "Come and we'll see how your shoe fits. We'll do an X-ray of your foot right there." So people were trying on different shoes and putting them on there. And someone said, "Stop that! That's too much X radiation for one body to have." I mean, if they had tried on 4 or 5 pairs of shoes that day, that could have gotten more radiation than a technician would have gotten in a month, so let's not do that, and they couldn't do it. We have done some dumb things before. That was before we understood how
it sounded like it makes sense.
Yeah, it really did.
X-ray signal.
Until someone said, that's too much radiation for a person to be getting. So anyway, that's the spectrum. And you see the relationship between frequency and wavelength. They go in opposite directions. Because, so anyway, that's the thing. But our good old atmosphere blocks most of that stuff, up to all that, most of this, and the visible light comes through. Now, here's what global warming is. Because the visible light comes through, as it does come through, the wavelength gets lengthened a little bit because it's losing some energy. And because the higher the frequency, the higher the energy. So it does, and then it gets trapped here as infrared radiation. That can't escape the atmosphere. They call that the greenhouse effect. Okay? That's what happens in your car. When I went to my vehicle this afternoon to drive over here, it was warmer inside than it was outside because the little bit of sun we got today was enough. The light, the visible light comes into the window of the car, but as it does, it loses energy and becomes infrared, and then it can't make its way back out. And that's why it's really dangerous leaving those pets, or especially young kids, in a car in the summertime if you don't have adequate ventilation, because the temperature can really go up. They call it the greenhouse. That's how greenhouses work. They have glass or plastic or something, and the light comes in, and even in the wintertime, keeps the plant warm inside because the infrared doesn't go back out. Okay. May be enough of that. All right. I think that's the last slide. No, here's one more. Oh, okay. This is the next section. Yeah. So that is the last problem. There is a physics connection evading radar, and radar stands for radio, detecting, and ranging, and laser stands for something else like that, 4 or 5 letters, words. I just don't remember what they are. And this is the stealth aircraft that technically kind of evades radar. It's built with materials that don't reflect very well. It has a very sleek, streamlined look to it, so it doesn't send much of a signal. That's just an example. Okay, problems here. Do any of the odds 1 through 17. Okay? Now, this is the part that y'all are probably be most interested in what you're doing. 16.3 sound waves. That's what sonography is all about. That's why we're doing this in the first place. Okay? Now, sound refers to those waves transmitted through a medium. Now, here's a key. Remember the electromagnetic radiation? It travels most efficiently through a vacuum, through outer space. That's why it can go from the sun to us, because there's no medium out there much. There's no air, there's no nothing. It's just space, But electromagnetic radiation goes through there really nicely. Now, electromagnetic radiation does go through air, okay, water, okay, normal things. Lead blocks most of it, okay? And different types of radiation will get. That's why the X-rays, they have all that lead shielding there to protect the technicians, okay? So, sound wave is a different kind of wave. It's a compression wave. It's not electromagnetic. And like we talked about before, didn't I, about if you have your hand in front of your mouth when you're speaking, you can feel a little puff of air. That's compressions and rarefaction. Compression and rarefaction. It's a pressure wave. It requires a medium. If we were in a vacuum, you wouldn't hear a thing I say, because it requires some type of medium to compress. Okay? Some sound waves, you might call it, are those that are emitted through earthquakes, and those are called seismic waves. and they have instruments, seismographs, that measure those. Now, the speed of sound is much, much slower than the speed of light. Speed of light is almost instantaneous. We talked about this last time. In a second, a light wave would go around the Earth 4 and a fraction times. I mean, that's fast, okay? Not instantaneous, but still very, very fast. Sound.
Said she knew a guy that could turn the light off and be in bed for something like that.
Now, what's this again?
A guy that could hit the switch and be in the bed before the light turned off.
I don't believe it.
Yeah, I never heard people say that little saying.
Yeah.
I can't remember what they
Well,
used it for.
I can almost believe some of the guys in here could be asleep before the light goes off, but you know. Yeah. But, yeah, no. Can't be that fast.
I can't remember what little, but she used that for something.
Yeah. It may have been science fiction or something. I don't know. But let's just make a comparison here. They have it in the text. The speed of light, remember, is, I got to get my pen back. Every time I change, I have to retrieve it. 3.00 times 10 to the 8th, isn't it? At least, yeah, 10 to the 8th meters per second. That's 300 million meters per second. Here is the speed of sound, approximately 331 meters per second. That's a million-fold order of magnitude, okay? No, nowhere close, okay? Now, that's why the old saying was that if you see lightning and listen for the thunder, when you see the lightning strike, start counting. 1,001, 1,002, 1,003. Count the number of seconds before you hear the thunder. That's approximately how far away, how many miles away the lightning strike was. Now, that's rough. It's not exact, but it's rough. Okay? Now, when they say this is the speed of sound, they say the speed of sound in dry air. Okay, more moisture you have in the air, the more it would compress. Okay? At 1 atmosphere of pressure. So if you're up on a mountaintop, the pressure is going to be a little bit less. And at 0 degrees Celsius. That's at the freezing point. I don't want to be out there then, okay? So anytime the temperature goes up, then the speed of light increases ever so slightly, okay? And as the temperature goes down, it drops ever so slightly. So here, I'm going to go back to my other slides because I don't have enough room to write here. So let me go back to this one and give you those conversions. Here is the speed of sound. Now I get my pen back. Okay. The speed of sound, again, this is dry air at 1 atmosphere of pressure, is given as 331 meters per second plus, this is a pretty small number, 0.61 meters per second per degree Celsius, okay, times your temperature measured in degrees Celsius. Now, if you got degrees Fahrenheit, you got to convert that to Celsius. So that's what you would have. Now, if you're dealing with Fahrenheit, then the velocity of sound in air would be 1,087 feet per second. Okay, now the difference here, there's more than 3 feet in a meter. So that's why this is more than triple. What were you going? Did you have a question, or were you just stretching?
No, I was just saying going up.
Oh, okay, right, yeah. But it's the same speed. It's just that you're measuring it in different units, feet per second rather than meters per second. A foot's about that long, a meter's about that long, so, you know, it takes a lot more. Okay? And your conversion then would be plus 1.1 feet per second per degree Fahrenheit. Okay? Now, what you have to do here is your temperature now in degrees Fahrenheit, but you have to subtract from that 32 degrees Fahrenheit. Now, why that? Because that's the freezing point of water. Remember, we said these numbers are at 0 degrees Celsius, which is 32 Fahrenheit, so you have to see how many degrees above freezing you are, and that's why it's T minus 32. Now, this T is Fahrenheit degrees, this T is Celsius degrees. Just have to keep that in mind, okay? Not the same thing. So if you're dealing with the U.S. customary system, that's the velocity. Metric system or SI system, that's the velocity, okay? So,
you said the top is the
SI or metric.
okay.
Yeah. The bottom one is U.S. customary. All right. So let's do example 1. Do I need to leave one of these up here? I'll leave them both. I think we got it. Find the speed of sound in dry air at 1 atmosphere of pressure if the temperature is 23 degrees Celsius. 23 degrees Celsius. This is your temperature. Now remember, most of the time, okay, this is a little confusing perhaps. In the last chapter, or maybe even in this chapter, we called the period of a wave capital T. Now we're calling temperature capital T. Time is little t, so the capital T's get used several ways, but you have to look at the context of your problem. This is a temperature, degrees Celsius. Okay? So which one of these would we use? The top one. Yeah, so it would be the velocity of the wave there. Sound there would be 331 meters per second plus 0.61 meters per second per degree Celsius times 23 degrees Celsius. So you see your per degree Celsius cancels out your degree Celsius. Now you're adding meters per second to meters per second. That would be good. So you first do this, 331 meters per second plus multiply those two together. If someone's got a calculator, you can just do the whole calculation at once, whatever you want to do. Plus 0.61 times 23. We'll just do the whole answer. 351. 351.13. Okay. Meter per second. Now, we don't need that many digits because the most we got is 3, so I would round that to 351 meters per second. Now, what did they get? Oh, I thought that seemed a bit high. Go back and check it again.
You said, okay, 331
1 plus 0.61 times 23. Times 23.
Oh, 23.
Yeah.
Okay.
What you get?
345.
Okay, that sounds better. 345? Point what? 33? 3, oh yeah, that's 345. Okay, meters per second. All right.
345.
Yeah,
Yeah.
345. What's that?
Oh, I had calculated it.
Oh, okay.
Put that on calculator.
Oh, I'm sorry. Should have wiped that out. Okay. I thought I had. Let me get my eraser so I'll erase it so it won't even be there.
Yeah. You just got to make sure you're using the right one. Right?
Yeah. Okay. That's example 1. Ready for example 2? Or you want that a little longer? Higher the temperature, the faster the speed. The lower the temperature, it slows down just a little bit.
Do a Fahrenheit one. With that minus.
I believe that's the... Nope, that's not the right one. Okay, let's do a Fahrenheit one. Okay. Goodness gracious.
They don't skipped all to another.
Is this the one you just said one example? Or that was the last?
I don't see a single Fahrenheit one in the problem set. Let's go to the back and see if there's one back there. Oops, wrong place. Review problems.
Maybe we won't have to use Fahrenheit. They try to tell us.
Oh, you can't bank on it. We can make up one. That is amazing. Why'd they give it to you if they're never going to require it? But let's do one. So you pick a temperature.
17.
Huh?
17 degrees Fahrenheit.
17 degrees Fahrenheit.
70.
Boy. Oh, 70 degrees Fahrenheit. Okay.
I said 17 the first time.
All right.
I had just said a number.
So the velocity is
That's a Celsius number.
is one. Yeah, that sounds like more of a Celsius number. 1087. That's feet per second plus 1.1 feet per second per degrees Fahrenheit times, what do you say, 70 degrees? 70 degrees Fahrenheit minus 32 degrees Fahrenheit, because you have to get how many degrees above freezing.
What's that? 1.1?
1.1 feet per second per degree Fahrenheit. So the first thing you got to do is your subtraction. What is 70 minus 32? 38. 38 degrees Fahrenheit. Okay. Now you can just enter your thing. 1087 plus 1.1 times 38. Because your degrees Fahrenheit will cancel out. It gives you feet per second. Add feet per second to feet per second. And what do you get? 1,128.
Yeah.
That sounds reasonable.
Oh, what are you?
Okay. Oh, 0.8.
29.
So you, yeah, range that to 29 then.
Okay, so we adding all of that up.
Okay.
Well, you add the first one and multiply the second.
Okay, wait. Yeah. Let me. All right. Well, my pen's not writing. Still not writing. There it is. All right. Yeah. First do the subtraction. Do y'all remember the little saying, please excuse my dear Aunt Sally?
Yeah.
Okay.
Parentheses first.
Yeah, parentheses first. That's in parentheses. Do that first. Okay. Then multiply the 30. Well, it doesn't matter the order then. Your calculators will do this correctly. 1087 plus 1.1 times 38. Because, see, the calculator knows to multiply before it adds. Now, if you did it,
Okay.
yeah, got it. Okay. If you did it this way, 1087 plus 1.1, and then do a times, open parentheses, 70 minus 32, close parentheses, it'll do that correctly
Yeah, I was
too.
gonna do it that way
You
too.
need to be sure you have those parentheses so the calculator will know to do that first. Please excuse my dear Aunt Sally.
Yes, that's
Okay.
old.
Yeah.
That's been around for decades.
Yeah. Well, I said it. They must be old. Okay, never mind. Okay. All right.
It was around when you grew up?
Yeah. No, actually, I learned it when I started teaching here. I think, you know. All right. No, it was before then. All right, let's go to example 2 then. So let me clear this. Can I clear this already? Okay. What is the time required for the sound from an explosion to reach an observer 1,900 meters away from the conditions in example 1? Okay. I just erased my answer, didn't I? What was the answer there? That was 345 meters per second. So the speed of sound in those conditions was 345 meters per second. Okay? So what's the time required for the sound from an explosion to reach an observer 1,900 meters away for those conditions? So the distance here is 1,900 meters. Now that's good to 4 decimal places, that second zero. Okay? But it doesn't matter because our other one's only good to 3. So it's fine, but it's not going to thing. Okay. Now, how do we figure out what the time is? Because that's the question. What is the time? Time is the unknown. Notice time is little t, always. Capital T could be period or it could be temperature, but this is just little t time. What's the relationship here?
Distance equals velocity.
Times time. You're absolutely right. Distance equals velocity times time. If you drive 50 miles an hour for 3 hours, you travel 150 miles. Yeah. Distance, velocity times time. So do you want to first solve for t, or do you want to plug in and then solve for t? Plug in, okay. Yeah, that's all, yeah, but make sure you divide by the right thing. 1,900 meters divided by 345 meters per second. Okay, wait, what? You got me off there by saying 3. Okay. 5.5. I'm going to call it 5.51. Now let's see what units. The meters are going to cancel out, and you're left with 1 over second, which when you flip and multiply, that just becomes second. A little over 5.5 seconds. Okay? And sure enough, that's what you get. Okay?
What they had? 5.5?
They got 5.51 seconds. Good for them. All right. Now, the denser the medium, the faster the sound, okay, travels. A sound propagates.
Why they put those thick cushions in like studios and stuff?
The big what?
The thick cushions. Like
Okay.
thick padding and stuff.
Okay, well now, yeah, because those are not very dense. They absorb sound, okay? So you don't get a lot of echo. That's why they do that. A lot of your music halls and things like this, they have those panels on the wall. They look decorative, but they're really there for a purpose to keep echoing from happening. Now, especially where you have things like domes and curved structures like the Capitol in Washington, D.C., there is a place there that if you whisper here somewhere way across the room there, they can hear you like they're standing right next to you because it reflects off, and it's called, oh, they have a name for that. I don't remember what it was. But then there are also places that you'll have dead spots. I don't know if any of you have been to the chapel on Samford's campus. It's Beeson Chapel, okay? A guy who goes to our church is an architect, and he designed that, and it's really a beautiful, beautiful chapel. But he was focusing on the beauty of it. There are a few dead spots in it, and if you sit right over here, you can hardly hear what the guy's saying. You sit further back, you hear him perfectly, but right here, because he has a big dome in it, it happens to be, remember, in last time we talked about constructive and destructive interference. It's a place where the node goes right there and you can't hear much. So they have put in some things to ameliorate that. But sometimes people get so focused on beauty they forget practicality. So I drive my wife crazy because I'm way more practical. She's very aesthetic. All right, so the next table that we see here is going to illustrate what we're just saying. If I can get it to come up, and that's this one. All right. As it said here, sound propagates faster in a dense medium such as water than it does in a less dense medium such as air. And here is a list of speed of sound in various media given here. Now, I would have thought that brass was denser than aluminum and that steel was denser than aluminum, but evidently they're not. Granite, okay. Alcohol less dense than water, so you see water has a higher speed of than alcohol. Air, very low, that's what we were just using. Remember, there's our numbers there. They rounded to 1090, whereas before we were using 1087, but the 331 is still the same. A vacuum no density, no sound. Okay? You don't have anything to compress. Now, if you remember, I don't know if y'all ever watched the old Cowboy and Indian or train robbers, sheriff type westerns. Yeah, the westerns, when either the Indians or the bank robbers or whoever it was wanted to know if the train was coming, they could stand up here and maybe you could hear it a few miles away. But they put their ears down on the track and you could hear it way further. Because the steel is denser than air, and you'll hear it much, much, much faster. I don't know if you've been underwater in a swimming pool, but it sounds like the sound is amplified there because the water transmits sound faster than the air does. So, all right. And that's what y'all are going to be doing when you do different sonograms of different parts. Did I tell you I've had a sonogram on something before? Did I tell you that one? Okay. I had a angiomyolipoma, which is blood, muscle, and fatty tissue. Lipo, yeah. Yeah. Some people have them, like I think I have one right here on my arm, a little fatty thing. I've had them before, but they found some on, I had a young doctor who was panicked about everything, and he thought he saw some how did it say? Oh, goodness. It is microscopic amount of blood in my urine, okay? Just minuscule. And he was convinced I had bladder cancer. So he sent me in for a sonogram so they could check it and see. Well, when they started, they said, your bladder is fantastic, it's fine, no problem there. But she just kept looking around. She said, but there's some shadow on your kidney, on your right kidney. Huh?
They just want money.
Yeah, that's what I think. So anyway, she started looking around. She called in her boss or whoever, and he looked too, and they said, we can't tell, but there's something fuzzy there. We'll have to do a more precise test. So then they did and we talked about this before, some type of a nuclear test that they put a isotope in there that would give off, and sure enough, they found angiomyolipoma, just tons of them around my kidney, but one of them had gotten big. It was about 4 centimeters, which is about close to 2 inches. And that was bothersome because the kidney is so vascular, of course it has to be. If that thing were to rupture, then I'd bleed to death internally before they'd ever know what was wrong, So they decided to take off the angiomyolipoma, the big one, and they had to take part of the kidney too because it was all in there. And so they took it, yeah.
I'm sorry, I thought she was through.
No.
But no, I have to deal with smart because my daughter was born with a cyst on her kidney.
Oh, I see.
But they was like, it's so dangerous because of the location where it is.
Right.
Just watch it,
Yes, exactly.
It's more dangerous to cut it off.
Right.
And like you said, if it flared up or ruptured,
right,
then that would be different.
Right, exactly.
They would take it off.
Yeah. So anyway, I had that operation, but boy, when I woke up and the incision started here and went all the way around there, I said, how many people do you have in there anyway? Well, what it was, he was it was UAB teaching hospital. He probably had his whole team in there looking at it, and messing around. So it was.
They couldn't give you a regular doctor?
Huh?
They couldn't give you a
no, a urologist. Yeah. He was good. He was really good, but he said they could have done a microscope. What are those? What do they call it? A very small incision and send the thing in. Laparoscopic. Yeah. But he said then we would have taken your whole kidney, and we wanted to leave as much kidney as they could. So.
But when they do ultrasounds, like I've had ultrasounds done, it don't look like they hit, like they it's no sound or nothing.
No.
They
It's
look at
all-
the computer
Computer,
like,
yeah.
like all the stuff.
All you're doing is reading echoes. It's just like a radar that measures how fast you're going. You know, there's nothing to see, hear, or anything else, but it's a wave. And that's the thing.
She would like tap it and then go to the next and scan again.
Roll a little ball.
Yeah.
And that's it. That's why it's ultrasound. Okay, you know, have you heard this? Dogs can hear frequencies we can't hear.
Mm-hmm.
Yeah, a dog whistle.
Right.
You blow on the dog whistle, you don't hear anything. The dog hears it, and it drives them crazy, you know, because different things have different frequencies. Ultrasound is very, very high frequency sound that we're not equipped to hear. I don't think any animal can. So therefore, it's not something that anyone will hear.
So you're
because
basically looking at the pictures. You got to know
Yeah.
the pictures and anatomy pretty well.
Right.
Yeah.
That's what they use for those dog chains, like my
Yeah.
neighbor got. Because, like, my daughter, she always play with their dog. But this one day, she went and picked them up and brought them over to the house. The dog was going crazy. They had put some collar on him to where it makes some kind of noise in his ear, like if he goes so far away from him.
Oh.
He acts so crazy, like on the chain.
Yeah.
But he was a cool dog.
Yeah.
So they got some kind of, I thought that was neat, but I never heard of them before.
Yeah.
You know what I'm talking about? Oh, see, I never heard of
Is
it.
it vibrate?
Okay.
They say it makes some kind of noise, like, just like he said. That on the
Okay. Now we have what they call an invisible fence, and that has a radio signal, and the dog has a little receiver, and we put it on every morning, and it has two probes, and it gives them a little shock if they cross that.
Yeah, see, but they say that theirs made a noise.
That made a noise. Okay.
Yeah,
Oh,
it's the
and
same thing, it's a little box.
yeah. Well, actually, this will make a noise too before you get to it, because that will warn the dog not to get a shock.
Oh, okay.
Yeah, so it does make a little noise at the dog. And in fact, our first dog, not first dog, the second dog, the first one we had that used the collar, she was such a wimp, big old beautiful dog, that after that, anytime there was a beep, 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 you know, like on a telephone or a camera or anything else that made any noise, she'd go nuts because she was afraid she was going to get a shock, you know. And she was so funny. If anyone had a camera and wanted to take her picture, I said, you can't have the sound on. She'll run the other way before you can get the picture made. We tried, my wife was trying to get a picture of her, you know, with me on the step. As soon as it went deet, 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 she was out of there.
The dog was going
Yeah.
crazy. Like, what are they doing to the
Yeah.
dogs?
All righty. So, some of the terms we deal with in sound. Now, I don't think this will be all that appropriate for ultrasound, but they may still use the same terms. Let's go back to the other slide. And, well, thought I could go back to it. There we go. I'll have to get my pen back. Okay. The first of these is intensity. My writing stinks, but I hope you can read it. That's the energy transferred by sound per unit time through a unit area. That's the energy, okay, transferred. I'm going to put Xferred, that stands for trans, okay, I just hate writing on this screen. Transferred by sound. Actually, it would be anything, light, laser, whatever, okay? Per unit time, also per unit area, okay? Per unit time and per unit area. This would be the intensity. In other words, how much energy, that's how much energy you get in a given time, but also covering a given area. Now, if you were to focus, for instance, that laser beam on the eye is very intense on a very small area, okay? If that were spread over, see, a regular light bulb would not be that intense because it spreads, but a laser it's focused, so it doesn't spread. And therefore, over a very small area, it can still be a lot of energy on a very small area. Remember, it's like the spike heel versus your regular shoe, a sneaker. That spike heel is going to be more pressure per unit area, even though it's the same weight of the person wearing the shoe. Okay, so that would be, and by the way, energy per time, if you remember that, that's power. So it's power per area. So the typical measure of this intensity would be watts per square meter, okay, or kilowatts per square meter, or something like that, okay? Now, the second of these terms, and this wouldn't pertain to ultrasound because you don't hear it, is loudness. Now, you would think these were related, and they are related, but they're measuring different things. It's the strength of the sensation of sound heard by an observer. The strength of the sensation of sound heard by the observer. Okay, now, if you worked at the airport, you know, doing something out there in the thing, notice all those guys and gals have the earphones, the sound suppressors on all the time, because if you didn't, you're damaging the loudness. But then those jet planes, when they're up in the sky, you don't hear them at all, or you hear just a very faint, because the loudness is a function of how close you are, okay? And they're way too close not to have those on.
What does that say?
Okay, which one? The second one, loudness?
Sensation of sound.
Heard by the observer.
Oh,
Okay, an observer. Okay. Now, let's go back to the concept of intensity. There are tables for this, okay? And again, it's watts per square meter is what we usually measure it in. And these are incredibly small numbers. Our ears are amazing. I mean, if you think this little puffs of air that I'm doing when I'm talking, you're way, way far. You can't feel those puffs of air at all, but you're hearing me talk, right? Your ears are incredible devices. Very, very, very sensitive. Okay? So the intensity levels, the threshold for hearing, let's see, I think we may have a slide on this, so let's see if we do. Yes, here it is. All right. Goodness, I'm still. Okay. All right. Threshold, watts per square meter. Of course, a watt's a pretty small amount of power, and a square meter is a pretty large area, so 10 to the minus 12 watts per meter, that's the threshold of hearing. Now, I can't hear that because my hearing's on the way out, but you can probably hear, right? And especially your kids can hear. Okay. Now, we'll get into this a little bit later. I'll come back to that. Minimal sounds, the threshold is scarcely audible, but minimal sounds that I don't hear, my wife hears, okay? She'll hear, she'll say, quit licking that bowl, okay? I don't know how she can hear that, but she does, okay. She's talking to the dog before, so, right, okay.
I was going to say, why was you licking the bowl?
It had ice cream in it, that's why. Okay, chocolate, okay, never mind. Okay. All right, I'm sorry, Rose. Okay. Minimal sounds like that, you know, people can hear. I can't, okay? A ticking watch.
Yes, this irritating.
Yeah. Don't worry, get older, you're not going to notice it, okay? A whisper, okay? Barely hear that, okay? In fact, this is so bizarre. She'll say, the timer on the stove, don't you hear it beeping? I said, no, I don't. So I get up to go in to turn off the timer, and I get about 5 feet from the stove. Oh, now I hear it. She heard it in the den, you know. It's a gender issue, I think. I don't know.
Who's
All right.
gender issue? You just
Okay.
ignoring it.
No, my hearing is terrible. Okay. But I do have selective hearing loss too. That's true. All right. Leaves rustling or refrigerator. Now, some refrigerators are worse than others. That's 10 to the minus 8 watts per square meter. Average home, neighborhood, street, that's moderate, just noises, normal stuff. Normal conversation, or the microwave beeping, that's about 10 to the minus 6. The car or alarm clock, city traffic, that's getting a little loud, 10 to the minus 5. Garbage disposal, vacuum cleaner, outboard motor, noisy restaurant, 10 to the minus 4, that's very loud. Factory, electric shaver, screaming child, that's getting, you know, and then there are lawnmowers, passing motorcycle, convertible ride on the freeway with the top down. Hair dryer, diesel truck. No, not hair dryers aren't usually that loud, but okay. Chainsaws are quite loud. Helicopter, subway train, you're getting up there. Car horn, snowblower, that's getting pretty loud. A rock concert, a propeller plane, you don't want to be too close to those speakers. 100 feet from a jet engine or air raid siren, you can do damage. Shotgun blast too close, you can really damage your ears. Okay.
So,
now,
so what would you have to have for it to totally be damaged? Like,
it probably depends, but if you're up in this, you can have it. It may not be, but it could.
I'm just wondering because I use my earplugs a lot. And
yes.
I don't want to
very good idea.
Issues.
I was the gunnery officer on our ship. Well, we went to I was gunnery officer on our ship, and I had to go to the practice on the guns. You know, go to the Navy school for that. And there's a 3-inch 50. The shells are about this big around, about this long. Those things were loud. Now, we were supposed to have the sound suppressors on, you know, but back then they weren't as good as what they are now. And you couldn't have complete because they were giving commands. So you have to be able to hear some things. So I imagine that contributed some to my loss. Also, I grew up on a farm. My dad operated chainsaws. I've operated a few. But I think my hearing was more sensitive than the others, and I think that probably contributed. But then when I was in the last ship I was on in the Navy was an aircraft carrier. And I was just behind the bulkhead for the hydraulic room that operated the jet blast deflectors. And what happens there, when you're launching a jet aircraft from an aircraft carrier, that's a really short runway. So they fire those engines up to full blast. The flames coming out of those are blue. I mean, very, very hot. If anyone was on the deck and that was happening, they'd all be fried. I mean, just like that. So what they have is these great big portions of the deck. After they bring the plane over, before they rev it up, they raise this portion of the deck at a 45-degree angle, and then the jet blast goes against that and goes straight up in the air, so people don't get burned or you know, blown off the deck or something like that. Well, the hydraulic system that operated those things was just ahead of the bulkhead, steel bulkhead that I slept again. I mean, the head of my rack was right there. So if they were doing night operations, you hear the planes taxi on that, it wasn't too loud, and then you hear them go, and you raise it up to this level. Then they crank up those engines. You know, it's a steel, and it transmits it really well. And we were the deck right below the flight deck, okay? And then as soon as the plane took off, you could hear the catapult throw it, because they also throw it off the plane with a catapult. And so it throws it off, and it takes off and flies. And then the jet blast effect, and they go, boom, you're right back down again. So if they were doing night operations, in the daytime I could deal with that. But at night operations, back then they had the little hard plastic ear plugs. And because I was already sort of hard of hearing, I think my ear canals were larger than normal. I put them in at night when I go to bed, and sometimes they fall out during the night. And then all that would be happening, I wouldn't even notice it because I got used to it. And I think that hurt too, because they measured on aircraft carrier, they'll measure your hearing when you first go aboard, they'll measure it when you leave, and they measured definite loss in that 1 year. And then we were in the yards too, where they had all the cutting and grinding and stuff going on. It was so loud, but I couldn't wear sound suppressor all the time because I had to be able to hear the phone ring. And if I had those on, I couldn't hear the phone ring. So it was really a bad situation. I did have hearing loss from it, so I don't know. And I think people who do a lot of riflery, firing guns a lot, if they don't wear something, they're going to have hearing loss. Actually, piano tuners, because they're hearing such high frequency sound really close, making distinction, they usually go deaf, or at least several of them. I've seen tend to that happen. Now, look at this range is what I was getting at. This goes from 100 to a billionth of a watt per meter squared, from 1 billionth to 100. That's a huge range of sound. Our ears can handle most of that, okay? Yours can handle more than mine. That's a huge range. So what they use another scale, and this is a log scale, logarithm scale. What a log scale is, it deals with the exponents, okay? And so therefore, every time you go down an exponent, they multiply it by 10, you go up by 10, okay? So from this is 10 to the minus 9, that would be 20, 10 to minus 10 would be 20, 10 to the minus 9 would be 30. So that condenses the scale to be 0 to 140. Now, basically, you don't want to be listening to too much past 100 decibels, okay? Anything within that, you're okay. But you don't want too much out here, okay?
Why would they put hair dryers with diesel trucks and stuff?
What's that?
They put hair dryers with diesel trucks.
I don't know. I didn't know hair dryers were that loud. I know you do it close to your ear, so that may be why they do it. Oh. I think these may be old too, because most hair dryers I don't think are that loud. But if the diesel truck, well, the chainsaws are really loud, so helicopters are really loud. So this is a log scale, and that's why something that's 100 times or 10 times as much is only 10 points difference. So it really scales it down. And that level is called decibel, and that's what dB stands for. Deci means 10 to the minus 10, 10 to the minus 1, deci. Bell, and why it's capitalized, is B-E-L, but they named it after Alexander Graham Bell, who invented the telephone. And they named the scale after him, decibel scale. And you'll hear when we refer to that. I don't know if they'll use that in sonography or they use another scale, because these are much higher frequencies than you'll ever hear here. All right. Now let's go back to the screen, the white screen. And unfortunately, the things that I had on it before have disappeared. Here's another term. Oops, let me get my pen back. Pitch. Okay? What pitch is of a sound is the effect of the frequency on the ear. Okay. Now, I usually think of it as meaning frequency, okay? But it's really the effect of frequency on the ear. If you hear someone, these really great singers, they'll say sometimes they have perfect pitch. And what they mean by that, what they hear and what they project is right on the money. Most of us, have you ever listened to yourself talk on a tape recorder?
Yeah.
Yes.
Did it sound like you?
Oh my goodness,
That's how it sounds.
Yeah. Here's why. You see, what you're hearing when you talk is actually what's coming through your bones, because your bones are really part of your system.
So it deepens your voice?
What's that?
Does it deepen your voice? Like the way you hear it?
Does what?
Does it deepen your voice?
I don't know. It just changes. I never recognize myself when I'm talking, and when I do, I say, "Ew." I don't listen to any of these lectures I give because I don't like the way I sound. Okay, I feel like these poor people because it doesn't sound that way to me. But a person who is a good singer, what she or he hears pretty much is what they project. And there's just something special about their structure that enables that. Okay? Now, there are also frequencies that I can't hear. And unfortunately, it's my father-in-law's voice is right in one of those frequencies. When he calls, I hardly ever can recognize his voice on the phone. Of course, when I'm talking with him, I know it's him. But when it's on the phone, I've gotten so I'm better at it. But, early on, I'd say, who is this? He seems to know me, because I don't recognize the pitch through the phone just doesn't sound right.
And how long you been married?
Well, this was early years. Yeah. By now, it's been quite a while. I can recognize him now because he has certain mannerisms that I pick up better. So that's pitch. Okay? Now, let's go back to, sorry that it's bouncing back and forth so much. Let's go back to the slide, and here's a picture of the ear. And again, this isn't something that probably you'll be worried with in sonography, but this is how it works. This is the ear canal. Like I said, mine's pretty large because I think I was born with some hearing loss. But see, all around this is bone. That's part of our system of doing. Now, it's pretty porous bone, so different people with different densities may be closer or further from perfect pitch. Here is your tympanic membrane. There's another name for that. The eardrum. Exactly. Tympan, eardrum. Okay. That's what receives the vibration first, but that's not all. It moves this little piece here called the malleus. It's attached to that. Think of that as sort of like a hammer, and this is the incus, which is sort of like the thing you're hammering against. And just very small vibrations here can be amplified greatly there. And somewhere here between, this is the outer ear out here, external outer ear, or exterior ear. The middle ear is this part here from the membrane through this part. And then you have what they call the inner ear. And that's really sensitive. And in the cochlea here, and in fact, my wife works with CMV kids, cytomegalovirus kids. She doesn't work with them, but she deals with the parents and things. That's where she's done her research. And those kids, if they detect the hearing loss early enough, sometimes they'll choose to have cochlear implants because CMV causes hearing loss, and it can be very, very severe. And some kids, that's why they're trying to do screening. If they can catch it early enough, they can do a lot of interventions. So you have places like the vestibule and semicircular canals and things like this, and then the cochlear. All this is picking up. They're doing different parts, and the fact that we can detect differences in very small frequencies in pitch and things, it's just absolutely incredible the way we're put together. And so anyway, that's basically. Now, what's this thing back here, the eustachian tube? You want to know what that's there for?
What is it?
Eustachian tube. It's behind the eardrum.
Drainage.
Okay, it has maybe a little bit of feature like the main thing that's good is to equalize pressure. Have you ever been driving in a car up in the mountains and then come down and you feel your ears pop?
Or you're rolling the window up on the interstate.
It can do that too, yeah. If you've been in a plane, quite often your ears will pop. okay? Changing elevations. What's happening here is if you go up in elevation, your internal pressure is one thing, the external pressure is less, and that puts a lot of pressure, because that's a very sensitive little membrane there, and you need something to equalize the pressure, and that's what the eustachian tube does. And if you've known kids with a lot of ear infections, sometimes they'll have to go in and widen the tube there, because if they get inflamed, then they don't, and then any changes. That's why kids sometimes on an airplane will be screaming bloody murder because their ears aren't adjusting. Their eustachian tube is too small that not enough air gets through to, or escapes one way or the other to relieve that pressure. Or they just like to scream. I don't know which it is. Okay. Probably both. All right, so that was 16.3. Okay. Let's move on to 16.4. This is the Doppler effect. Okay. So I think I'm probably going to have to go back to, going to have to go back to, no, that's not it. I keep hitting the wrong buttons here. Okay, back to my other slide here. Get my pen back. Okay. What the Doppler effect is, and you've probably heard this before, there's a few classic examples of it. If either you're moving toward something that's making a noise, more likely it's moving toward you. But if for any time there's relative motion between it, if it's coming toward you making a fixed sound, it actually sounds like the frequency goes up. Or if it's moving away from you, it sounds like the frequency goes down. Now, don't confuse this with the loudness. The amplitude, yeah, for sure, it gets louder as it gets closer and gets fainter as it moves away, but listen to the pitch, and you'll see that happens as well. That changes, and that's because of what they call the Doppler effect. Named after a Austrian, Christian Johann Doppler. He first described it, okay? It's a variation in pitch. And here is the basic formula for it. We're probably going to have more than one, but here's one. F prime, we'll talk about what this is in a minute, is equal to F. Those are both frequencies. These are velocities. V in the numerator and V plus or minus Vs in the denominator. Okay. Weird looking formula. Here's what these things stand for. This is the actual frequency of the sound. The actual. Okay, let me sort of draw the picture over here too. Here's the object moving, and what happens is the sound waves in front get pushed closer together, but those in the back get spread further apart. Okay? So you have a compression in front and a rarefaction in the rear. Okay? So this is the actual sound waves coming out of the object. This could be a train whistle as the train's coming at you really fast. It could be an ambulance as it's doing. Now, they sometimes actually, they vary the pitch anyway, but if it was a solid pitch, this is the actual frequency of the source, actual source frequency. Okay? That's usually a fixed frequency. Okay? Now, what this is your Doppler shifted frequency. This is what you hear. It sounds like it's changing. The reason is the source is coming to you. It's forcing the compressions to be closer together, so it's going up in frequency. Okay? And then when it's going away from you, they're getting further apart, so it's going down in frequency. So this is your Doppler shifted frequency. The frequency you think you're hearing. And you are hearing it, but it's shifted because of that. So here's what the V's are. This is the actual speed of sound. And sometimes you'll have to adjust that for temperatures like we did earlier. Okay? So both of these are the speed of the sound itself, 331 or 345, whatever it happens to be, that be meters per second, or 1900 or 119 or 120 feet per second. This, though, is this velocity of the source. If the source is moving this way, this is the V sub s, the velocity of this, or the speed of the source. The speed of the train as it's coming toward you, of the ambulance as it's coming toward you, or whatever it happens to be, okay? Or moving away from you. And that's why the plus or minus is down there, okay? Now here's what you have to sort of wrap your head around. What happens when the denominator increases? What happens to the number? Like if you go from 1/2 to 1/3. The denominator increased, but what did yeah, it went down. Okay? So if you have the minus sign, that makes the denominator smaller, so that's increasing the frequency. So that's when the plus sign in the denominator is when the source is moving away from you, which is sort of backwards feeling. The plus is source moving away. The minus sign is when the source is moving toward you. Okay? Away from you or toward you. Okay? And that's because, is it making the denominator bigger or smaller? The minus sign makes it smaller, so it's getting louder, so it's moving toward you. And the sign being plus makes the denominator bigger, which makes the frequency go down. Okay? So you have to sort of keep that in mind. Okay. Now, I think this next slide is on the other one. Sorry, we're going back and forth like crazy here. Okay. Get this one back up again. Yeah, here it is. All right. Here are two people standing by the side of the road. They're not in the road. Standing by the side of the road. Cars going down the road. And for some reason, their horn is stuck. So it's going at a constant frequency. But as the car is moving toward this person, it sounds like the horn's going, it's going up in frequency. But this person over here, now of course it's getting louder too, but I'm talking about the frequency. For this person over here, it's going down in frequency. And the reason is the waves are getting pushed closer together, increasing the frequency, moving further apart, decreasing the frequency. So that's where that formula comes into play. Depends on whether the source of the sound is moving toward you or away from you. So here is, that didn't last long, did it? This is example 1. Okay, go back to this and get my pen back again. Okay. An automobile sounds its horn while passing an observer at 25 meters per second. So what would that be? In that equation we had earlier, what would 25 meters per second be? Of the source, because that's the thing making the noise. The automobile sounds its horn while passing an observer at 25 meters per second. The actual horn frequency is 400 hertz. The actual horn frequency. What would that be in your equation back there? The actual source frequency would be just the F, without the subscript. Okay? Assume that the speed of sound is 345 meters per second. So that would be your V. V is 345 meters per second. Remember, that's the one we had at what, 20 degrees or something like that? 23 degrees, I believe it was. So this is that same type situation. Okay, there's your setup. A. What is the frequency heard by the observer while the car is approaching? So it says, what is the frequency? So this is your F prime. The Doppler one, the one that you hear. Not the one it's actually doing, the one you hear. And that will be what? Okay. Remember the actual source frequency times V over V. Okay, but which do I use? That's the key. While it's approaching you, which one would that be? That's the minus, because it makes your denominator smaller. Minus Vs. Okay? That's the one we use here. Now alright, good deal. That little spike in it made it look like it might have been a plus. So, the actual frequency was 400 hertz times your velocity of sound is 345 meters per second divided by 345 meters per second minus the source speed, 25 meters per second. Okay? Now you do that subtraction first. So that would be 400 hertz times 345 meters per second. Subtract that there, and that's going to be 320, right? Meters per second. Notice your meters per second go out, and you wind up with something in hertz, which is exactly what you need. That sounds pretty reasonable. 335 hertz. Oh, 375. Okay, I thought it was a pretty big increase. What's that? 375 hertz. That sounds reasonable. Better than 345, but they got 373 in the book. Okay, I don't know where that discrepancy came from, but 373 is what they have in the book. Okay. Whoops. I'm sorry. No. If you did the minus, that's not 373. The minus makes it go up. I can't find my pen. Eraser. Yeah, get out of there. No, it's supposed to be the minus, and but something is wrong with your calculation, I think. Okay, and here's why: because you see this number is greater than 1. 345 divided by 320, so 400 times 345 divided by 320. That has to come up something greater than 400. Because this number here is greater than 1. 400 times 345 divided by 320.
Yeah, 400 times 345 divided by 320. 431.
It's what?
430.
Yeah, oh, okay, 431. Yeah, okay. I thought you said 3.
431.25.
Okay, that rounds to, well, I would have thought that rounded to 432. Yeah, that's right. The frequency goes up because it's coming toward you.
How did they get 373?
No. You're looking at the next one. Yeah. Okay. That's the B part.
Yeah.
The B part then says, what is the frequency heard when the car is leaving? So now again, you're looking for F prime. That's the Doppler shifted frequency, and that's going to be the same 400 because the car horn didn't change. It's just your perception of it changed. And now, and the speed of light or sound didn't change. 345 meters per second over 345 meters per second. But this time you're adding, because you're making the denominator bigger to make the frequency smaller, you're 25. Still going at the same speed, meters per second. That was 25, wasn't it? I believe it was. Yeah. Okay, so this will be 400 hertz times 345 meters per second divided by, that would be 370, wouldn't it? I believe it is. Okay, so they're rounding that to 373 hertz. Very good. All right. Now, the thing closest to what y'all will be doing here indeed is a physics connection ultrasound. Well, that's the page of your book. And look at the frequency of that. 20 kilohertz to 5 megahertz. Guess what, team? That's nowhere close to the things we're talking about here. 373, 340, 400. That's nowhere close. Okay? It's used for diagnostic purposes in place of x-rays because it does not use radiation. Safer for the person and the fetus or whatever else being examined. There's a picture, three-dimensional ultrasound of a human fetus. It's just incredible that they can get those kind of images. The computer is doing a lot of that, okay, to do that, but you still have to know how to operate it. Well, that finishes 16.4. There are problems at the bottom of the page there. I'd say do any of the odds 1 through 5, and then on the next page, any of the odds 7 through 19. Okay? You do what you think. All right. Let's move on to resonance. All right. You may have heard people talk about certain things resonating. Okay. Now, we use that term sort of generically, but, oh, I can resonate with that or something like that, meaning it's something I react to or respond to well. Well, in sound, resonance is a little more specific, but it's pretty close to that. Okay? I think I'll use this screen for a bit. All right, to erase this example. Okay. What we call the natural frequency of an object. Okay, natural frequency of an object, such as a tuning fork, and they have a picture of that. I'm trying to think if they have that in the book. I'm in the slide set. Let me see if they do. I think they might. Let me see. I'm going to lose it if I do it. No, they don't. Goodness gracious. Shucks. Okay. So let's go back. But if y'all got books, so I didn't mean to do that, but I did it. Okay. I'll come back to it later. Okay. I got to get my pen back again. Okay. There's so many sort of examples, I can't think of which one would be the best for this, but they show a picture of a guy playing a guitar. You know how the frets are on the guitar? What he's doing is holding down the string against that, so it effectively is shortening or lengthening the length of that guitar string where it is. And that's going to send out different frequencies when you pluck it. So when you put it here, it's one note. When you put it up there, it's a lower note. Down here, it's a higher note. Okay? That's sort of, well, it happens a lot. You did the clarinet. Remember, we talked about opening and closing the valves. That's going to change those frequencies. Well, the natural frequency, probably of that cornet or the guitar string, he tunes it, right? And you have to have a good ear to do that. I never could. My mom never took a note of music in her life. I could never tune a guitar. She could sit down and get it tuned and nothing flat. But it was a lousy guitar, and it went out of tune every day. So finally I quit. I said, I'm not even interested. I can't do this. I have to have my mother tune the guitar for me. I had no ear for it at all. So what resonance is when you hit that frequency, do y'all remember this commercial? It was Ella Fitzgerald hitting some really high note and breaking a glass. Y'all remember that? Okay.
I don't know who that is.
Huh?
It's a singer.
It was on TV.
Singer,
yeah, it was way before your time. But anyway, what it was, if you hit that frequency perfectly, and it happens to be the natural frequency of the object, then it starts vibrating, and the vibrations, remember when we talked about constructive interference, they start constructively interfering and growing. Now this has several characteristics. Remember I said the piano tuner. What he had was tuning forks, which are set to very specific frequency. So when he would strike a note on the piano, if it was this tuning fork's note, the tuning fork would start vibrating a little bit, okay? Because it picks up on its natural frequency, okay? That's resonance. Now you can also do this. Have you ever pushed somebody in a swing? Okay? Now, do you push on them right when they're coming toward you? No. That's hard on you and it's hard on them. What you do is wait till it gets to the top of the swing and then push. And you don't have to push very hard and then they go higher because you're pushing right with the natural frequency of the swing. Have you ever tried to push off a car? You haven't. So you watch someone do it. You'll push on it and then relax. And then right as the car starts moving ahead, you push a little more, relax, and push a little, and after a while, you got it moving. You can push a car, okay? Because you're using the natural frequency of the car and pushing at just the right moment, so you're resonating with the car's natural frequency. Well, that's what a lot of things with sound does too. And in fact, they have here the singing wine glass, okay? I don't know why we turned it on, but we happened to land on an old movie, Miss Congeniality. Do you remember that one? Mm-hmm. Okay, it was a dumb story. I can't think of her actress name now, really famous actress. Goodness gracious. But she played this really coarse, gross, but great-looking FBI agent. And they had heard that there was a beauty contest that there was some sort of danger at, and they had to get an inside person. And even though she was coarse as all get out, she was the only one good-looking enough to go undercover in a beauty pageant. So that was the story. Her talent was making wine glasses sing, and she was going to play something on the wine glasses. And of course, the other contestant started drinking the water out of them, and she couldn't do it. So she did something else, which is throw her around her FBI agent partner. But anyway, that was a dumb thing. But you can do this because the crystal in the wine glass has a fixed frequency. And that's what when Ella Fitzgerald hit that really high note, if it happened to be the frequency of the wine, she could break the wine glass. And that was it Memorex or was it her? So anyway, that's what resonance is. No problems in it, just a description of it. Now that leads then to what they call simple harmonic motion. And so many things in our everyday life depend on simple harmonic motion. If you think about it, your sleep cycle. You sleep so many hours, you're awake so many hours. The sunlight, the temperature, everything goes in periodic cycles. At night, the temperature drops most of the time. In the day, it goes up most of the time. We just get used to that. The tides, they come in, they go out. They come in, they go out. Simple harmonic motion. Every musical instrument uses simple harmonic motion. When you hit the note right, you've got a good wavelength there. And when you're off just a little bit, ooh, it doesn't sound good, does it? I used to play in the cracks. Never mind. So what do we mean? Here's the definition for simple harmonic motion. And that's harmonic. That sounds like sound, doesn't it? Simple harmonic. This is really ugly writing. Motion. Okay, simple harmonic motion is a type of linear motion. Now, that might need a little description there. Okay? In which the acceleration of an object is directly proportional to its displacement. Acceleration of an object directly proportional to the displacement from equilibrium position. I'm abbreviating like crazy. Equilibrium position. Classic illustration of this is a spring. When you stretch a spring a little ways, there's the force you're pulling against. Spring's pulling back, trying to go back to its equilibrium position. Or when you compress a spring, it's pushing against you, trying to go back to its equilibrium position. But let's imagine what's happening there. Okay, let's say we have a spring. It's probably easiest to picture one vertically. Okay? Let's say you have a weight on the spring, and wherever it sort of settles out, that's its equilibrium position. So what I'm going to do is pull down on it. The spring's pulling back up, so as soon as I release it, it's going. Now, down here at this place, the speed is 0, right when I release it. Now, the spring's pulling back, exerting a force on it, accelerating it back to its equilibrium position. But guess what? It's at the maximum speed when it gets there, so it overshoots it. And then goes back down, and then back. So this is simple harmonic motion. The maximum speed is at the equilibrium position, but that's when the force goes to 0. When it starts compressing again, now it's pushing downward, slowing it down again until it stops it here and pushes down and then gets it going. So it just does this. Have you ever ridden in a car whose shock absorbers weren't very good? Okay, you hit a bump and you do this for a while because you're in simple harmonic motion. Now they dampen out after a while, but that's what a shock absorber does. It shortens that. It ends that simple harmonic motion very, very quickly. Okay? So that is an example of simple harmonic motion. Now there's a couple of terms that we deal with that. Number one is they call the displacement. I used it up here, displacement. And that would be, the magnitude of this is called the amplitude of the wave. And we talked about this before, right? The amplitude of the wave is the maximum displacement from the equilibrium position. That's how much it's displaced. The period, we talked about that before too, that was a time period. So that's the time of one complete vibration. These are a review almost. Now what does that mean? If it started here, it would go down here and back up again. If it started here, it would be up here, not to here, back till it's going in the same direction again. That would be one complete vibration. Okay? Now remember, that was our other capital T, was the period. Okay? You just have to keep up with which one it is. Okay? Whereas frequency then, which we talked about in other things too, frequency is the number of vibrations or cycles in a given time, as in per second. So remember, the period is the time it takes for one cycle, whereas the frequency is the number of cycles per unit time. So they're exactly reciprocals of each other. Remember, frequency is 1 over period, and period is 1 over frequency. Okay? Those we had before. All right. Those are the key terms. Let's hit this last slide, and you'll see another example of simple harmonic motion. Remember, I hit the wrong button. There it is, chapter 16. And it disappeared on me. Here we go. Welcome back. Okay. This is the one we were doing, or it was going to be next. Okay. Now, a Ferris wheel actually is simple harmonic motion. But remember, it's at linear displacement. Ferris wheel is going in circles. But if you think about it, if you call this his equilibrium position, sometimes he's up, sometimes he's back, and sometimes he's down and back. So this would again be a linear motion here. How far above or below is equilibrium position we would be. Now, simple harmonic motion of the shadow of a person, that would be here. If the sunlight's coming here, right now his shadow's there. A little bit earlier it was here. And as he moves over, it's going to be there, and then it'll be here, and then it'll move back. His shadow would move in simple harmonic motion. So many things in nature follow simple harmonic motion. Okay? His altitude, the shadow's movement, all those things would be happening in simple harmonic motion. And just the Ferris wheel itself, as it's going at a constant speed, simple harmonic motion. All right. Afraid we're out of time, aren't we? Okay, what we'll do is start next time with the pendulum. Okay? Whoa! There won't be any more slides next time either. Now, one thing that we'll note here, we came that close to finishing the chapter. So we'll finish the chapter next time. Do some of you want to have the test to start working on it? Okay, well, let me make the copies of it. I may have some copies here. Let me see. Okay. That's acceleration. That's work done. Work done. Work done. Here we are. Stretching is... No, that's... There it is. Okay. All right. I don't have my master, so let me go back. I think there's 9 people left in the class. I'll be right back. 3 of you remain. 3 of the 4 that you showed up. So thank you for. All right, there are a couple. Oh, good deal. Thank you. You need something to grade, huh? Thank you very much. Okay, no, just kidding. All right, there are a couple of corrections to make on it. This test bank is really poor. Question 8 and 9. It has to do with Doppler effect. A train traveling at a speed of 80 miles per hour approaches an observer at a station and sounds a whistle. What frequency is her? Hey, you need to know what the frequency of the whistle is. They forgot it, okay? That whistle is at 585 hertz. The whistle is at 585 hertz, okay? So you answer the question from there. They tell you, assume what speed of sound. Okay, now, and by the way, on that, notice you got miles per hour, but the speed of the sound is given in feet per second. You got some units to deal with there, right? Okay, so you got to do a unit conversion there first. Okay, number 9, same deal. Car traveling away from you at 70 miles per hour. Car horn produces a sound, a frequency of blank. It just left out the thing altogether. Put in there, I put it in 5,000 hertz. What frequency do you hear? Okay? Now, we haven't done number 10 yet. So don't worry about 10 yet. We'll do that next time, and then after that you'll be able to do number 10. So don't sweat on 10 yet. You could do any of the ones 1 through 9. Okay? The clock doesn't start on it until we finish the chapter next time, but I thought if you wanted to get started, you certainly can. All right. Then I will end this. Any questions? Yeah.
Test 3.
I'm sorry?
Test 3.
Oh, you didn't get test 3? Okay, let me find it. Goodness, I thought you were here every time. All right, you too. Thanks. That's test 1. That's test 2. That's test 3. Okay, test 3. This is 50,000 pounds. I've never seen 50,00. That's 50,000, and that's 60,000. Okay. So I tried to make that correction on it.
Thank you.
All right, good deal. Okay.